Hi there. In today's series of videos, we'll talk about cancer and various aspects of it. In this first video, we'll talk about the incidence of cancer in our populations. We'll talk about mutations that give rise to tumors. We'll talk about two different fundamental types of mutations that cause cancers. And then we'll also end with a brief discussion about other types of chromosomal abnormalities that can lead to cancers. The framework for most of our discussion about cancer and the way you should learn to think about it is derived from a seminal paper by Doug Hanahan and Robert Weinberg called The Hallmarks of Cancer, and they identified 6 different biological processes that cancer cells in which they behave differently from normal cells, and this will be the focus of the second video, but I just mention it now. And this paper is made available on the course website, and it's essential reading. On this slide, we see a graph of cancer incidence versus age, and what it shows us is that a person age 70 is much more likely than a person age 40 to be diagnosed with cancer in a year's time. So an incidence is an annual rate, and this is the first clue that there might be an accumulation of DNA damage that accumulates over a lifetime that eventually, when you pass a certain threshold, might give rise to a cancer. The lifetime risk is currently at approximately 1 in 3, and along with cardiovascular disease is the 2 biggest killers in Western countries, in which deaths due to infectious disease, poverty, and malnutrition have been reduced significantly. Lung cancer is the leading killer, and it kills as many people as the next 5 most prevalent cancers, which include breast, prostate, ovarian, colon, and stomach cancer. Women have approximately a 1 in 9 chance at getting breast cancer. Men have roughly a 1 in 3 chance of getting prostate cancer if they live long enough. In the case of prostate cancer, many of these cases might be well tolerated and are often not the cause of ultimate death of the patient. This slide relates some basic facts about cancer growth and its implications for detection and diagnosis. By the time a cancer is detectable, meaning it's a little larger than a millimeter, it's been growing for a long period of time. Microscopically, the tumor is established and mutations have accumulated. It also explains why sometimes the courses of cancers are relatively brief, in that there are relatively few doublings that need to occur until the mass of the cancer becomes unsustainable. Furthermore, as mutations tend to accumulate, the time it takes a cell to double decreases. So 10 doublings that would occur between 25 and 35 will take much less time than the doublings between, say, 1 and 10. Nevertheless, the best thing you can do for any type of cancer in any organ is to detect it early. Almost any tumor can be treated rather successfully if it is caught very early. I think all of us appreciate that our lifestyles have big impacts on our risks of cancer. For lung cancer, which again is by far the most deadly cancer, the overwhelming largest risk factor for the development of cancer is smoking. And what we see here are the cumulative lifetime risks on people who have smoked, probably a minimum of about 5 or 10 pack years, but then show the benefits of quitting smoking. Significant drops in risk for stopping earlier rather than later. While I understand that ages 65 and 75 seem like an eternity away to you now, at that point when it seems like those years are very precious, there's little you can do about the fact. So urge everyone to consider minimizing the impact on your later health by modifying behavior. Particular types of molecules in the environment can negatively impact our chances for getting cancer. For instance, aflatoxin, which is one of the most potent mutagens, it's involved in peanut butter mold. It forms covalent adducts with nucleotides, and these nucleotides are interpreted incorrectly by polymerases or are unable to be processed, and hence will cause mutations to arise. These are another series of molecules which their cancer-causing effects have been amply documented in lots of literature. We talked earlier about the effects of UV radiation, and in modern society there's almost no way to live an entirely risk-free life, but being aware of the exposures and attempting to minimize them makes good sense. Now, as we've sort of hinted at previously, mutations in different genes have different effects. I'd like to consider two basic classes of cancer-related genes. One are proto-oncogenes that, if mutated, become oncogenes and will actively cause cancers, and genes that in their normal function are tumor suppressor genes. They inhibit the cell cycle. When they get mutated, they are no longer able to suppress cell cycling, and those will lead to cancers. A useful analogy for these two classes is in an automobile. This is the equivalent of the gas pedal. This is the equivalent of brakes. So oncogenes, if you step on the gas pedal, if you increase the activity of an oncogene, that's going to be more likely to cause cancer. Whereas if you inactivate the brakes, that's what's going to lead to cancer. And here's on the top, we're going to look at oncogenes, and here we'll look at tumor suppressors. Again, overactivity mutations, gain of functions, dominant phenotypes. If an oncogene gets activated, just a single copy of it, that's going to be enough to drive the cancer. That's hitting the gas pedal with at least one foot. In loss of function or recessive mutations, if you have a mutation and you inactivate one copy of the gene, there's still a second copy present on the other chromosome. And so this will continue applying the brakes to the cell cycling, and cancer will not yet form. So it takes a second mutation in activating the second copy of the gene. Now the system has no brakes. Now cell cycle can proceed when it shouldn't and lead to inappropriate growth. Additional events have to happen, but these can often be the starting points, because as we talked about, the time of doubling for cells can change. When you get these particular mutations, the doubling times can increase, so cells that are already slightly damaged are produced more rapidly, and then they tend to accumulate, allowing for even more opportunities for further mutations until you start ticking off all of the 6 categories that we showed on the hallmarks of cancer slide, and that was what will eventually lead to a cancer. RAS is an example of an mutated oncogene. When mutated, remember, it cannot hydrolyze GTP to GDP, so it stays active. It continues to signal. It's going to activate the MAPK pathways, and this is inappropriate signaling because the ligand has not bound to the receptor tyrosine kinase, which is the normal signal for causing growth to occur. If you have a non-mutated form of RAS from the other chromosome over here, it doesn't matter. The signal is going to fire anyway. Retinoblastoma protein, or RB, is an example of a tumor suppressor. Remember, it's going to bind to proteins that are necessary to transcribe genes in order to proceed to S phase, to pass the start checkpoint. If you inactivate one copy of RB, the other copy is present, still applying the brakes, still binding these transcription factors. It's only when the second copy of retinoblastoma is mutated or inactivated, and then you can have inappropriate expression of genes that will lead to progression to the S phase of the cell cycle. Historically, retinoblastoma is an important case for the evolution of our understanding of cancers. In the early 70s, when Alfred Knudsen formulated the Twohit hypothesis, and it was based on the observation of people who developed retinoblastoma. He noticed that there were 2 classes of retinoblastoma. There was hereditary retinoblastoma, which tended to run in families, and then there was non-hereditary retinoblastoma, which appeared sporadically in populations and didn't run in families. One of the things they noticed is that in the inherited cases, or the cases that ran in families, people often developed tumors in both eyes. For the sporadic cases, people only generally develop a tumor in one of the eyes. And what Knudsen was able to realize is that if you inherit a copy of a defective retinoblastoma gene, That means every cell in your body has that, and any one of those cells which develops a second mutation can go ahead and lead to cancer. So any of the cells, a single additional event hitting that retinoblastoma gene will cause cancer. In the non-hereditary cases, you have to have a particular cell get 2 mutations in the same gene, and this is the square of an unlikely event leading to a very rare event, and that's why this is much less frequent in the population. Now, another type of problem with your DNA or chromosomes that can cause cancer are translocations, in which material that's normally on one chromosome gets transferred over in an improper recombination and gets transferred to another chromosome. And in chronic myelogenous leukemia, CML, there's again a famous type of chromosome called the Philadelphia chromosome, which is recognized by its very short appearance. And what we've learned, when things cross over, we're putting some genetic material near other genetic material, and this is an instance where proximity matters, and the molecular details are on the next page. Here we see 2 genes, and this is the breakpoint to the formation of the Philadelphia chromosome. We have a upstream and a promoter region of one gene. In this case, it's a B cell receptor gene. This is a very strong promoter for B lymphocytes. ABL is a tyrosine kinase that participates in growth pathways, phosphorylating downstream proteins that leads eventually to cell cycling. And when you have the translocation, you put this aggressive, very strong promoter region on top of this kinase growth promoting gene. And so you're going to get a lot of copies of a growth promoting gene in B cells where the promoter is most active. Translocations can run rampant in cancer as a sort of runaway effect occurs and cells start segregating very poorly when dividing. I would say that the majority of cancers have vastly disturbed karyotypes, but here, as far as I can tell, this is an entirely normal looking karyotype. However, it's claimed that there are mutations. Obviously, to get to a situation like this, you have mutations in DNA repair genes, you have mutations in the checkpoint genes, both the G2 to M checkpoint and the metaphase to anaphase checkpoints are obviously not working well, and that's one of the reasons why mutations to proteins like p53 that are in charge of regulating cell cycle arrest can be so conducive to tumor formation. Inspired by the Knudsen Twohit hypothesis and careful analysis of the histology of colon cancers in very many different stages, along with molecular characterization, Doug Fearon and Bert Vogelstein identified that a number of different genes that were mutated at various points in tumor progression. And this was a landmark paper for a number of reasons, but also leading to the idea that once one mutation occurs, cells divide a little more quickly so that the cells with the mutation get overrepresented, then another mutation occurs, and then now you have a clonal expansion where genes with those particular mutations are dividing much faster than normal cells, and eventually you'll have runaway accumulation of mutations leading to metastatic cancers. This will set the stage for the next video where we discuss the formalization of these concepts in Hanahan and Weinberg's paper about the 6 hallmarks of cancer cells. Okay, thank you for listening.